Hi everyone. Today we are going to start our new course on CBSE Class 9 Mathematics, and we will be starting with number system as our first chapter. Throughout this entire course of 20 weeks, we would be covering all the chapters in the syllabus of CBSE, and following which we will be also covering a lot of practice exam questions that would have appeared in the past. So let's start right into the number system chapter. So this first chapter, let's just dive into this topic of number system and see what exactly are the different type of numbers that we find on a day-to-day basis. So as we would have started during our elementary days, we would have come across various numbers like number 1, 2, 3, 4, which we call as natural numbers. And as we progressed over the years, we realized that natural numbers are part of a series which also includes zero. And along with zero and natural number, we call them as whole numbers. Now, what whole number means is anything that can be counted on a number line starting from zero rightwards. We can call it as whole numbers, and we can plot it on a number line easily in form of various units over a period of time. They can span up to infinity, hence it's a continuous line. Now there are also numbers which are mirror images of these numbers, and hence we can say these are the negative integers which replicate the entire behavior of these numbers but on the negative side. So for 1 we have a -1, for 2 we have a -2, and for 3 we have -3, and so on. And together all these series of numbers that we see on a number line, these are called as integers, and these integers are represented by a alphabet called Z. And what we mean to say is anything that can be represented on a number line in whole numbers to the right are set of whole numbers, and anything to the left are negative integers, and together these form a set which is integers. Now there comes a scenario where we would realize that all that exists in this world is not only in form of whole, or say numbers which can be counted. There would be numbers which would be in form of fractions, or as we may say in form of p by q. Now when we say p by q, p and n can obviously be any of the numbers that we just saw in form of integers. So let's just again look at various scenarios of rational numbers, or say numbers which can be depicted in format of p by q. So we may have a number like 2 by 3, which is obviously in format of p by q. So we may say this is a rational number and is the simplest form. So, and the only I would say restriction over here is q can never be equal to 0, because that would make the number undefined. So if we say 2 by 3 is a rational number, 4 by 6 again can also be a rational number because it's also in a format of p by q. But this again can be simplified further as in 2 multiplied by 2 and 2 multiplied by 3. So if we simplify it further in the simplest form, this again is 2 by 3, which we just saw earlier. So any number that can be mentioned in format of p by q is a rational number. Now, how do we depict this on a number line? Let's just try and see if we can do that also. So now, for instance, we just saw we could draw a number line from 0 to infinity on the right side, and if we want to portray this number p by q 2 by 3 on the number line, what we need to do is we need to understand that that number 2 by 3 is obviously somewhere between 0 and 1, because when we divide 2 by 3, the entire number would mean it is less than 1. So let's just do one thing. We can just divide and see how it appears when we do a simple division on in terms of numbers. So obviously we would have to take a decimal because 2 itself is smaller than 3. So when we take a decimal, we identify that it would be divisible, the quotient would be 0.6 in order to arrive at 18. So the next number would be 20 again. So as we keep on repeating this, we would identify that the number would keep on repeating from 0.6 onwards. So this is a decimal format of the rational number that we just saw, and 0.66 is somewhere between 0 and 1 is what we understand. So we can say it is 2/3 of the distance between 0 and 1. This is where 2 by 3 would lie. Similarly, let's look at an example where we can say if a rational number can exist between two rational numbers. So for instance, a number on a number line, 2 and 3 are also rational numbers because we can write them as 2 by 1 and 3 by 1, right? So what would be a rational number in between 2 and 3? Should be somewhere in between 2 and 3, right? So the best way to identify what is a rational number between 2 and 3 is to just add up these two numbers, which is 2 and 3, and divide by 2 because we are trying to find the midpoint. So what this would mean is we have 5 by 2 or 2 whole 1 by 2 as the number, which is the rational form midpoint of these numbers 2 and 3, and this would be somewhere exactly in between 2 and 3. So we can actually find out a lot of such scenarios where these points would exist, and obviously these are not finite set of numbers which would exist between, say, any two given numbers. The numbers of rational numbers between any two given numbers would always be infinite because we can call out any such rational numbers between these two. So there is no finite number of rational numbers that exist between two numbers. Now let's just look at a couple of examples and also try to refine further our understanding that we just had. So consider a scenario where we want to identify between two specific numbers on the number line. Let's say again on an axis where we have negative integers now from 0, -1, -2, -3 and onwards. What would be a scenario where we want to identify three rational numbers between 0.2 and -2 and -3? So these would obviously be 3 points. This would mean there are actually 4 gaps in between. So the easiest way to find out these 3 points between any two numbers, three rational numbers between any two numbers, is to identify the number of gaps, that I would say. So if we are trying to identify three specific rational numbers between two integers, all we need to do is add one more to the number that we want to identify. So we are trying to identify three rational numbers, so adding one would mean we have 4. Now all we need to do is from 2 we keep traversing 1 unit at a time towards 3. So we take 1 by 4 of it. This means it is -9 by 4. The second number would be twice of the same, which is -10 by 4. The third number would be thrice of it, which is -11 by 4. The fourth number that we see is 3 itself, because when we do a 4 multiplied by 1 by 4, all we have is -3. So these are the three numbers that appear between -2 and -3. To put them in sequence, we would have -9 by 4 here, we would have -10 by 4 over here, and -11 by 4 over here, in the entire sequence between the negative integers -2 and -3. Now let's take one more example and try to just implement what we had learned right now. And if we want to say specifically see 5 rational numbers between say number 3 and 4. So now if we plot them as separate units on a number line, this would be something as it would appear on a number line. Now between 3 and 4, if we want to find 5 specific rational numbers at an equidistant point, we would obviously have 6 gaps appearing on the number line. So what we would do, for us the n right now is 5, number of gaps would be n plus 1, which is 6. In order to find all these points, what we need to do is just keep on adding 1 by n to 3 every time in a sequence to identify these numbers. So our first number would be 3 plus 1 by 6. Second would be 3 plus 2 multiplied by 1 by 6. Third would be 3 plus 3 multiplied by 1 by 6. Fourth would be 3 plus 4 multiplied by 1 by 6. Fifth would be 3 plus 5 multiplied by 1 by 6. And as we come to sixth, this becomes 4 itself when we multiply 6. So these are the 5 numbers that we want to plot between number 3 and 4, which would be 3 whole 1 by 6, 3 whole 2 by 6, which would eventually mean 3 whole 1 by 3 if we simplify it further. This would be 3 whole 3 by 6, which is actually 3 whole 1 by 2. This, and then it would be 3 whole 4 by 6 and 3 whole 5 by 6. So this is the simplest way to find any number of rational numbers between two given rational numbers. We just tried to solve two different problems. Similar way we can identify and keep solving for any number of rational numbers that we want to identify between two different rational numbers that is provided to us. We can actually take a couple of more examples, but I want to keep the first session pretty light, and what I would end up doing is maybe solve few of these problems and host it for you through YouTube shorts for you to maybe clarify or have a better understanding of these scenarios. Now when we look at decimal representation of rational numbers, we just saw rational numbers can be anything which can be portrayed in a format of p by q, right? Now consider a scenario, we have p by q, and if we write it as 1 by 2, it would obviously mean we can also call it as 0.5. And how did this 0.5 appear? Is basically if we divide 1 by 2, what ends up happening is we have to take a decimal to make it 10, and then when we multiply 2 by 5, we have 0. We have 10 and the remainder is 0, so obviously the quotient is 0.5. So any number which is rational mentioned in a format of p by q can also be depicted in a decimal format. Now how do we keep doing this is something pretty simple. As we just saw, we divided the entire number as a basic mathematics operation that we used to do during our primary classes, and we can identify obviously how do we depict this particular number in a decimal format. So let's take up a couple of more examples and see how does it come up converting a rational number into decimal format. So right now let's see, if we want to convert 5 by 8 into decimal, all we need to do is divide 5 by 8. Since 5 itself is smaller than 8, it is not divisible. We take a decimal, and then we obviously take 6 in the quotient and we get 48. The number is down to 2. We get 0 again from here, and then we do a multiply the quotient of 2 with 8. What we receive is 16. The remainder is 4. We take a 0 more, and then we have a quotient of 5. So what we end up getting is 40. So 5 by 8 in decimal format would come up to be 0.625. So we need to understand that anything which is rational mentioned in a P by Q format also has a decimal format to it. Now the variation to this is a decimal may be a value which is terminating. So for instance, we had gotten 0 after certain number of iterations through this division and we end up at 0.625. There would be scenarios where earlier we just saw that when we divided 2 by 3, we keep on getting a number which is not terminating. So what we say is this is a non-terminating recurring decimal format of a rational number. So let's again try to see if we can also do some hands-on around non-terminating decimal numbers. So for non-terminating recurring decimal numbers, there are certain examples that we'll take up. Before that, I'd like to clarify how do we ensure or we are sure that any format, any rational number in format of P by Q, is it terminating or is it non-terminating? So in order to guarantee that if this number is terminating, we need to find if the denominator or Q is a prime factor of 2 and 5. So how do we guarantee that? So let's see few more examples and if we can confirm if this would be a terminating or a non-terminating sort of a scenario. So first example would obviously be, say, something like a 27 by 80. Now when we say 27 by 80, 80, if we simplify it further, it would be 27 by say 5 multiplied by 16, which would be 27 divided by 5 multiplied by 2 raised to the power 4. So since it is a prime factor of 5 and 2 alone, this would always be a terminating rational number, a terminating decimal format for a rational number. Now, whenever there is a scenario where this denominator is not a factor of 2 and 5, we would end up having a non-terminating recurring decimal format for a rational number. So these are few examples that we just saw in order to cover the basics. Now let's see few examples where this would be a non-terminating number. So consider an example where P by Q can be written as for an example or a number of 3 by 11. If we divide 3 by 11, what we end up getting is something that doesn't terminate. So when we say it doesn't terminate, we obviously have a decimal and then a 2, which means we have 22, and then we have 7 where it comes down to 3, we have 2 again, which gives us 22, and this sequence keeps on repeating because it is a repetition of the same activities that we keep on doing. So what happens is if we divide 3 by 11, what we end up getting is 0.272727 eternity. So the best way to write this down is 0.27 bar, which means the 27 is something that would keep on repeating as a sequence after the decimal. So let's take one more example and we'll conclude this specific section of conversion of rational numbers to decimal numbers. So consider a scenario if you want to divide 11 by 6. This obviously is a rational number because it's in a format of P by Q. Now how do we find the decimal format of this? Let's do a division, simple division of this. Now we can say when we divide this by 6, we have 5. Now 5 is no more divisible by 6, so we take a decimal. After placing a decimal, we take a 8, and what we get is 48. Now for number 20, we take 3 again, and this keeps on repeating itself. So what we just saw is 11 by 6 is 1.8333, which keeps on repeating. So we can write this as 1.83 bar, where 3 is the number that keeps on repeating throughout. All right. So let's ensure that we are sure what we have learned for rational numbers in terms of both terminating and non-terminating recurring scenarios. So after this, I'd just like to call out that for every rational numbers, a rational number can be terminating or non-terminating, as we just saw, and any decimal number that we have can also be represented in form of a rational number p by q or vice versa. So we converted p by q into decimal. Now let's consider a scenario where we have 0.25. How do we convert this number into a format of p by q? Pretty simple. What we have to do is just multiply this decimal number in order to make it a whole number. So if you multiply it by 100 and divide it by 100, the number would still remain the same. So what it does is it ends up becoming a fraction in itself. As we multiplied 100 in the numerator and denominator, it's multiplying as good as multiplying this number by 1. So this is 25 by 100. On simplifying it further, if we divide it by 25, what we end up getting is 1 on top and a 4 in the denominator. So what this ends up doing for us is converting this entire decimal into fraction or in a rational format of p by q. So let's also deep dive and see a couple of more examples, because what we just tried to understand is a very simple terminating decimal number into a rational format. Now how about trying to see if we can actually solve for a scenario where the decimal number is non-terminating and we want to actually simplify and see if we can convert it into a rational number. So consider a scenario where we have 0.57 bar, which means this decimal in itself is non-terminating recurring number. So this is a never-ending sequence of numbers. So what we do is, if we assign a variable x a value same as the number provided to us, and then we take 100 of x, what it does is shifts these two values before the decimal. So we still have the recurring number, but we have a whole number before the decimal. Now since we already know that x is 0.57 bar, we can just subtract this from 100, and what we identify is 99x would be 57. So x in turn would be 57 upon 99, which if we simplify it further, dividing by 3 would be 33 and 19. So 19 by 33 is the rational form of 0.57 bar. This is as simple as that. What we need to ensure is we are able to convert this recurring non-terminating number into a whole number first before the decimal, and then subtract it to ensure that we are able to arrive at a rational number. So let's take few more examples so that we are confident. So consider a scenario where we have, say, 2.4178 bar as non-terminating decimal number. How do we convert it to p by q? For this specifically, if we assume that x as a variable has a value of 2.4178 bar, and if we take, say, a factor, or we multiply x with a number of 1000, what it ends up doing is shifts 4 numbers from the left and gives us 2417.8178178 and so on. Now what it would do is, if we subtract these two, it would end up giving us a number where we would have 2.4178, and as it keeps on repeating, so this portion would get eliminated, and what we would have is as basic as 0.4 and 2415. So we are left with 999x. So x in turn would be 2415.4 divided by 999. If we multiply 10 to the numerator and denominator, it would end up appearing as 24154 upon 9990. This is the rational form of the decimal number 2.4178 bar. So there would be a lot of such questions that we'll have to practice in order to ensure we are confident with this scenario. Now, as we are sure and right now we understand what a rational number is and how it gets converted into a decimal number, let's try to understand what are irrational numbers. Now we saw that rational numbers are something where the number can be represented in a format of p by q and can be further converted into decimal numbers which are either terminating or they are non-terminating, where we just put a bar on top to ensure that we are conveying the right message of this number getting repeated after the decimal number. So irrational numbers are those where the decimal format of the irrational number itself doesn't even terminate, it doesn't recur in a sequence. So we cannot guarantee or say that xy would keep on repeating. The format would be such where we may have 1.4142 and so on, which is a square root of 2. So these are the numbers where we cannot guarantee that the number would keep on repeating itself in a format of uh, a recurring sequence, which we just saw earlier. So that makes a number irrational. So let's just dive deep and understand that how does a irrational number work. For that, what we would do is basically try to solve for, say, square root of 2 and see how the sequence comes out to be. So let's do a long division method square root derivation for number 2. So imagine the number 2, we try to take zeros as we learned in the long division method earlier during our previous classes. So 2 in itself would not have square root, so what we do is we take a square of something lower, which is 1. So as we take 1, what we have is 100. Now we have the addition of these 2, which is 2. Now as we get into the decimals, what we do is we cannot multiply it with 5 because 25 multiplied by 5 would be 125. So all we can do is multiply by 4, which would give us 96. As we multiply by 4, what we are left is with 400. Now as we add these two and come up with 28, we cannot take 2 because this would give us 564. We have to go with 1. So as we take 1, what we are left is basically 119. Now as we have 119 and we get 2 more zeros, we have 282 already. So 5 multiplied would mean 14,000 odd numbers. So we will have to go with something which is, say, smaller than 5. So we go with 4. As we go with 4, what we have is 6, 9. Yeah. We have 11296. So as we subtract 11296 from 11,900, what we have is 60400 again, and we have 2828. So we cannot take 3 because this would add up to 84, so we take a 2. So as we take a 2, this it would mean we have number 64565. So what's happening basically, as you see, is we have 2 again over here. So this number is not repeating itself. It is keeping on expanding, but it is not getting terminated. So square root of 2 would mean it is 1.4142, so on, but it doesn't end at a number, neither does it gets repeated in form of sequences. So we can say square root of a number which is not a perfect square root would always be irrational. Similarly, for square root of 3, square root of 7, all these numbers, square root of 9 obviously would be 3. So it is a rational number, but square root of 6, square root of 5, the numbers which do not have a perfect square root would obviously mean that they are irrational. So some examples are square root of 2, square root of 3, square root of 5, square root of 6, of 7, of 8, and so on. Now there are certain properties of these irrational numbers. So for instance, if we have an irrational number which is square root of 2, a negative of this is also an irrational number. Similarly, the sum of two rational numbers and a irrational number would also mean that they end up being irrational. So consider a scenario where we have a rational number like 2 by 3 and we have an irrational number like square root of 2. This again would be an irrational number. So to simplify it further, it would be 3 root 2 plus 2 divided by 3, which is irrational. So the property of irrational number is if it gets added to a rational number, it makes it irrational, and if it gets added to an irrational number, it is still irrational. And we just saw that a negative of a irrational number is also irrational number. Now the product of an irrational number and a rational number would also make it irrational. So this is an irrational number, this is something which is rational. Now when we multiply these two, the product in itself is something which is again irrational. So irrational number in itself, when it gets multiplied to a rational number, would mean that the product is irrational. Now consider a scenario the opposite is not always true. When I say that, consider if an irrational number like square root of 2 is multiplied by an irrational number square root of 3, would give us square root of 6, which is again irrational. But how about multiplying two irrational numbers by itself? This would be a rational number. So the opposite of what we discussed in the previous section is not always true. So a rational number multiplied up by a irrational number would obviously give you a irrational number, but an irrational number when multiplied with an irrational number doesn't always ensure that the product is irrational. It may or may not be rational. So let's look at a few examples and see that how this entire logic of commutative, associative, and distributive laws work on the rational numbers. So when I say commutative, I would obviously mean that A plus B would mean B plus A. So going by the law of commutation, A plus B should always be equal to B plus A. So if there is a number 2, square root of 2 plus square root of 3 is same as square root of 3 plus square root of 3. Similarly, if we go by the law of additive identity, anything that has 0 added to it would obviously not change the identity of the number. So 0 plus square root of 2 is same as square root of 2 plus 0. Now let's look at Now this was the additive identity. So let's look at an example for the associative nature of real numbers. Uh, so any irrational number is also associative in nature. So for that matter, if we have square root of 3 plus square root of 2 plus 3 plus a number 4, this is same as say square root of 3 plus square root of 2 plus 3 plus the number 4 itself. So both of these when added together would be the same result as something that we just saw on the RHS. So all these rules of mathematics applies to irrational numbers as well, and you can perform these exercise on your own to see it for yourself that actually there is nothing complex about these kind of scenarios that we just saw. Let's look at couple of examples to see hands-on in terms of how the addition subtraction works in irrational numbers. Now before that, there are a couple of rules for multiplication of irrational numbers, as well as even for that matter division as well. So if we have two different irrational numbers a and b, it is same as writing both of them within the square root. Similarly, if we have say a rational number within the square root which makes it irrational, this is same as writing square root of a upon square root of b. So these two are very basic rules of multiplication and division when it comes to application on irrational numbers. Now let's solve for a few examples, and we'll be fairly comfortable in terms of the mathematical operations on irrational numbers. Now consider a scenario where we have square root of 2 multiplied to 3 and 7 root 3, and if we have to add this to another irrational number of square root of 2 minus 5 multiplied by square root of 3, what exactly would be the answer? We can open the brackets and arrange it sequentially to make it simpler for us to factorize. Now since these two have a common factor of square root of 2, we can say 3 plus 1 after we take root 2 as common. Now we can take square root of 3 as common, and we can say this is 7 minus 5. So the final output would be 4 root 2 plus 2 root 3. So as we saw earlier in terms of basic operations on irrational numbers, we can do a basic addition, even multiplication of irrational numbers. The only challenge with them is that they cannot be depicted in a terminating or non-terminating recurring format of decimal numbers. They do not have a specific ending in terms of sequence of decimal numbers. All right, so let's solve for a few more examples in terms of certain CBSE questions that would have appeared in the past in few of the exams questions. I'll also ensure that we are posting a lot of these practice questions on YouTube Shorts as well. So let's take an example where we have to divide 16 root 2 by 4 root 2, and since root 2 is common, we can specifically cancel them out. Now 16 upon 4 has a common factor of 4, so the result for this is 4. Let's take one more example which is a bit more complex, where we say we are trying to divide 12 root 15 with 4 root 3. Now as we have seen, it is same as 12 by 4 multiplied by root 15 by root 3. Going by the rule of division that we saw earlier, we can say this would be 3 in itself multiplied by square root of 15 upon 3, as 3 cancels out 15 and ends up being root 5. So the final result is 3 root 5. So we can solve all these such questions with basic mathematical operations, and it is not as complex as it may seem. So there are a lot more operations of mathematics that can be performed on rational numbers, which are to do with, say, even exponential calculation, having square, cubes, or even to the power of 4, 5, 10, or any other number. How do we operate with that? I think as we go along this entire series of uh, class 9 CBSE syllabus for mathematics, we will just come along these scenarios and solve for it. So before we end this session on rational and irrational numbers, I'll just also try to plot the irrational number on a number line to show you how exactly it appears. So as we just saw in last few minutes, we could plot decimal as well as rational numbers between two numbers pretty easily, just by taking uh, the midpoint, or say the number of gaps between the required points, and identifying these numbers. Similarly, we can also plot irrational number like square root of 2, square root of 3, square root of 5 on a number line. So let's try to do that and see how it comes along. So I'll maybe just use a scale to plot a straight line, and what I'll do is also maybe plot the units on this straight line and see how it. So say if this is the origin for us, this is first unit, second, third, fourth, fifth, sixth, and so on. Now with sixth we have the line going on till infinity. Now if this is the origin for us, this is number 1 on the number line, number 2, number 3, number 4, and number 5. What we need to do is now also take a unit length of right angle triangle side to see if we can actually create a right angle triangle with two sides of unit 1 each. Now consider a scenario. I'm trying to plot a right angle over here, and if we draw a hypotenuse with these two lines having length of 1 unit each, as per Pythagoras theorem, obviously the hypotenuse would be sum of square of these two numbers. So what we have is square root of 1 square plus 1 square, which is equal to square root of 2. Now this square root of 2 is obviously longer than number 1, but it is not as long as 2 itself. So if we consider this as a radius of a circle, and if we use a rounder or a compass to plot it as an arc of a circle, it should cut somewhere around this point, which should ideally be the length of square root of 2. Now a similar thing can be done to find out square root of 3. So as we found out square root of 2, maybe if I plot one more right angle to this, considering this as the base for me, and how about adding one more unit of 90 degree to this, and maybe I try to extend this as the hypotenuse. So if this is 90 degree, this would be 1 unit for us, and this as a base is root 2. This entire length would be square root of a square plus b square, which is 2 plus 1. which should ideally be the length of root 3. Now if we take this as a radius of a circle and draw an arc, this would obviously exceed our previous square root of 2, and it should be somewhere over here, and this was earlier square root of 2. Now if we keep doing this, what would end up appearing is a square root spiral for us. Now let's just try to extend this further and see if we can plot, say, a 90-degree side to this rectangle. So if I plot this as a straight line as one of my base, and I join this further to 0, this again is unit 1. Our base earlier was square root of 3. What ends up appearing is 3 plus 1, square root of 3 plus 1, because we have a square of a square plus b square. A square is square of square root of 3, and b square is square of 1 itself. So what ends up appearing is square root of 4, which is number 2 itself. Now if we consider this as a radius of a circle and draw an arc, this would exactly meet us at number 2 on the number line. And if we keep extending this further, as in with a base of 2 and a right angle side of 1, again with a 90-degree, what we have right now would be square root of 2 square plus 1 square, which would ideally be square root of 5. So this would be square root of 5. If we use this as a radius and extend it further, this would supersede the number 2 on the number line and end up somewhere around here. This entire length would be square root of 5. This is a pretty interesting thing that you can try with your compass and geometry box yourself, and represent this square root of various numbers on a number line. I hope you like this entire video. What I'll do is maybe I'll solve a lot of these examples that we just discussed and post it in form of YouTube shorts, so that you can consume it in short, crisp formats, solve for these questions and be fairly comfortable with the topic. So in the next session, what we will do is try to cover the exponential properties, rationalization properties of irrational denominators and irrational numbers, so that we will be able to complete at least the number system in the upcoming couple of sessions. Thanks a lot. Thank you for your time. Don't forget to like and subscribe to this channel as we keep on continuing in this journey towards completion of CBSE syllabus